Every autumn, a tiny bird weighing less than a coin leaves the Arctic tundra and flies to the Antarctic, alone, at night, without a map, without anyone showing it the way. And then, in spring, it comes back, to the same field, sometimes to the same tree. You probably assume there's a simple explanation, some kind of compass, a sense of direction baked into the brain. And that's partly true, but the real answer is stranger and more extraordinary than any simple explanation could contain. Because birds don't navigate, not in the way that word implies. They don't follow a route. They don't consult a map. What they do is something that neuroscientists and physicists are still working to fully understand, something that might involve sensing the quantum structure of the Earth's magnetic field with their eyes. Let's start with what we know. The first piece of the puzzle is magnetoreception. Birds have the ability to detect the Earth's magnetic field, and for decades, researchers assumed this worked like a compass. A tiny cluster of magnetite crystals, iron-based particles that physically align with magnetic field lines, found in the beaks and inner ears of many birds. The magnetic pull would orient the bird the way a compass needle orients to north. Simple, mechanical, elegant. But the magnetite hypothesis ran into a problem. The magnetic sensitivity documented in birds seemed too precise, too adaptable, too responsive to minor field variations to be explained by a simple mechanical system. Something else had to be involved. In the 1970s, physicist Klaus Schulten proposed an idea so strange it was largely ignored for decades. He suggested that the magnetic compass in a bird's eye might work through a quantum mechanical process involving pairs of electrons in a light-sensitive protein called cryptochrome. When light hits the cryptochrome molecule in the bird's retina, it creates what are called radical pairs, electrons in a quantum-entangled state whose spin states are influenced by magnetic fields. The orientation of the Earth's magnetic field would subtly shift the chemistry of these radical pairs, giving the bird a visual representation of magnetic field lines, literally allowing it to see the magnetic field overlaid on its visual world. This idea, called the radical pair mechanism, was considered exotic for years. Then researchers started testing it. Henrik Moritzen at the University of Oldenburg has spent decades studying the navigational biology of migratory birds, particularly the European robin. His experiments found that when birds were exposed to weak electromagnetic interference, the kind produced by ordinary human electronics, their magnetic compass became completely disrupted. But the disruption only affected the cryptochrome-based light-dependent compass, not the magnetite-based system. The two systems are distinct, and the light-dependent quantum-based system appears to be the primary compass. In other words, the European robin may literally see where north is, not sense it through feel, not orient through vibration, see it as a visual overlay. But a compass tells you which direction is north. It doesn't tell you where you are or where you need to go. This is the second piece of the puzzle, something researchers call the map. The magnetic field of the Earth isn't uniform. It varies in intensity and in the angle at which it intersects the ground, what scientists call magnetic inclination. These variations create a kind of invisible geographic grid, and there is compelling evidence that birds can read this grid to determine their latitude and, to some extent, their longitude. This would give them not just a direction, but a position, a true map. Researcher Henrik Moritzen and his colleagues, along with teams led by Joseph Vilchko at Goethe University in Frankfurt, have spent decades building evidence for this map and compass model of bird navigation. The map tells the bird where it is. The compass tells it which way is which. And together, they allow a tiny Arctic tern to navigate from pole to pole without ever having been taught the route. But there's a third piece: smell. At least in some species. Researcher Anna Gagliardo at the University of Pisa has documented that homing pigeons deprived of their sense of smell lose their ability to navigate home, even when their magnetic sense is intact. Her work suggests that birds may build olfactory maps, memory structures based on the gradient of sense carried by winds from different directions, as an additional navigational layer. The bird effectively memorizes a smell landscape of its territory, and then there are the stars. Researcher Stephen Emlin, who conducted landmark experiments with indigo buntings in the 1960s, placed young birds in a planetarium and showed them an artificially rotated night sky. The birds learned to use the rotated star patterns as their reference for north. Even when those patterns were completely artificial, they weren't born knowing the night sky. They learned it. They identified the fixed point around which all other stars appear to rotate, which in the real world is Polaris, the North Star, and used it as their anchor. Remove the stars, and the star-based compass goes dark. Restore them, and it reactivates. So, what does a migrating bird actually do when it flies south in autumn? It appears to integrate multiple redundant navigation systems simultaneously: magnetic field geometry, quantum visual perception, stellar rotation patterns, olfactory landscape memory, the sun's position and polarization angle. Infrasound, the low-frequency sound waves produced by ocean waves and mountain ranges that can be detected from thousands of miles away. And learned landmarks, particularly near the final destination. Each system can fail individually. The stars are hidden by cloud cover. The magnetic anomaly over a certain region disrupts the quantum compass. The smell of smoke from distant fires distorts the olfactory map. But the redundancy means the bird rarely fails entirely. It compensates, it integrates, it arrives. And here is the detail that researchers find most remarkable. Many of these navigational abilities are not fully innate. Young birds appear to have a genetic predisposition toward the correct migration direction, a rough heading inherited from their parents. But they then learn and calibrate that heading using their own experience of the magnetic field, the stars, the smells, and the landmarks they encounter. Migration is not just instinct. It is instinct combined with learning, combined with memory, combined with a suite of sensory tools that human technology is only beginning to understand. The bird weighing less than a coin, flying alone at night from the Arctic to the Antarctic, is not following a path. It is constructing one in real time, using a sensory toolkit so sophisticated that it involves the quantum mechanics of electron spin states responding to the magnetic field of an entire planet. And every autumn, without fanfare, without maps, without anyone watching, it gets there.